Okay, so here's our dilemma then. So we want to determine, yeah, you see how this works here?
No, I don't get that one.
So Sydney is driving this, she's pedaling up here, and she's winding up, as she pedals, she's winding up this rope, which is attached to the end of this lever, which pivots right down here. Okay, so there's the hinge. There's another line attached to that that goes up over this pulley, which just changes the direction, but then it goes over this system of pulleys, like so, and then attaches to the box, right? And we want to know what is the overall theoretical mechanical advantage for this system. Okay, I got to give you some measurements here, right? So let's say that we know that the radius of the pedal, so this distance right here. Oops. What did that do? Oh, I think it's on zero. Oh, I can't. I know what it is. I can't write out the top. Oh, listen, I know what it is. So this distance right here is, let's just say that that is 15 centimeters. 15 centimeters. And we know that the radius of the tire is 20 centimeters.
Wait, why is there a difference between the tire and the, what was that?
Well, because she's pushing on the pedal.
Oh, the pedal.
Purple's the pedal,
I get
right? Okay. And the overall length of the lever, so from there all the way down, is 4 meters. But this distance right here is 2 meters. Okay? And we'll just go ahead and attach a weight to this. We're going to say our mass, this is 100 kilograms. Okay?
Upwards.
Upwards. Yeah. See, this is hooked to the ceiling, and these are movable pulleys.
Oh.
Okay. See how that works? Yeah, right. It's just resting on the ground right now.
Okay.
Okay? So how are we going to do this? How many simple machines are represented here? 3. Yeah. So we've got a wheel and axle,
Yeah.
right? Okay. We've got a lever. What class lever? 3.
1.
It is a second class lever. Very good. It's like a wheelbarrow, right?
I don't, wait, what I don't get for the lever
Oh, hang on here.
is when you pull that thing, the lever up.
Yeah, hang on. So we got to have one little, you're right. I messed something up on the
So
lever.
it slides.
Yeah. You're right. You're right. So I got to make one little change-a-roo here. So this one is going to go down here, like,
You gotta put it below the wheel. The rope going on the wheel. Pretty sure that's
I'm going to put it right here, and I'm going to have, I'll show you, I'm going to have, yeah, I'm going to do this. I'm going to have, I'll show you. So this guy's got to go, you buddy, there you go. So he's going away. Yeah, you're right. You saw something. So it's going to go like this. It's going to go. Large. Like that.
There you go. There you go.
Okay?
Good job.
So all this pulley did was just change the direction of the force.
Yep.
Agreed? Yep. Okay. Much better. Okay. So we've got a wheel and axle. We've got a second class lever, right? And then we've got a block and tackle or pulley system. Okay. What is the mechanical advantage, the theoretical mechanical advantage of each of these? But before we do that, let's just review something really quick. Let's review something. So if we go back to our ramp the other day. Okay, I can do this. Oh, this will be kind of cool. So there's my. And so let's say that this ramp is 2 meters high and 10 meters long. If I'm gonna push a box up this ramp, we know that the actual mechanical advantage is the ratio of the output force to the input force, right? It's what the machine actually does for us. We always want to write mechanical advantages in terms of how many times the force is multiplied, because usually that's what we want to do. Usually, the vast majority of the situations, we're trying to use a simple machine to be able to input a small amount of force and get back a big amount of force, right? Okay. So actual mechanical advantage equals output force, what the book would call resistance force, over input force, which the book would call effort force, right? Okay. What about theoretical mechanical advantage? Okay, so it's going to be, has to do with the distances, right? The distances through which the work is done, right? And so the theoretical mechanical advantage is going to be the input distance divided by the output distance, right?
How distance doesn't matter for
Say it again.
how distance doesn't matter for pulleys.
Well, okay, so it's hard with the pulley, we have to interpret it in a different way. And there are some tricks we can play on this. But in general, that's always the way it's going to be, right? So what this means then is the theoretical mechanical advantage in this case is going to be 10 meters over 2 meters, which is 5, right? Everybody agree? Okay. So 5 to 1 or 5. So theoretically, we're going to multiply the force by a factor of 5. Now, in actuality, that may not be the case, right? In actuality, there's going to be probably some friction involved, and so if we actually measured the output force to the input force, it probably ends up being something, I mean, who knows, maybe it's 3 to 1 or something, right? There's going to be some loss there. And if we want to calculate efficiency is just telling us what percentage of the useful input work is actually being translated into output work, right? And so efficiency equals, one way of calculating it would be actual mechanical advantage over theoretical mechanical advantage, right? What's the other way of calculating it? I think I just told you, actually. Yeah, so output work over input work. Make sense? Okay, so the moral of the story here, though, is that the theoretical mechanical advantage had nothing to do with the actual forces that we experienced. It was based on maybe a picture of the machine. What did we anticipate? Based on the physical dimensions of the machine, the physical characteristics of the machine, what did we anticipate in a perfect world theoretical mechanical advantage would be, right? Okay? So sometimes with a ramp, it's really easy to see input distance and output distance, but it's not so easy to see that with, for example, a pulley system, or with even a lever. It's not so easy to see that, right? Things like that. But we can always come up with some substitute for this equation that's going to be easy to calculate for any simple machine. So if we go back to our picture, okay, what about up here? Well, in this case, these are, remember, a wheel and axle is really just like a round lever. It's like a lever that's, does that make sense?
Yeah.
Okay. So technically, the 15 centimeters and the 20 centimeters really aren't the distances that were the forces applied through, but they're proportional to them. Agreed? They'd have to be, wouldn't they? Right? Because we know that the actual circumference of the wheel is proportional to the radius of the wheel, right? Does that make sense? So yeah, we're going to be pushing through a circular motion, but it's proportional to the radii of the two the two circles. And so we can substitute actual input and output distances for something more convenient. In this case, just the radius of each wheel. Radius of the wheel and the radius of what we might call the axle, right? So what's the theoretical mechanical advantage going to be for the first simple machine then? So TMA1 equals what divided by what? We said it was always going to be the input distance divided by the output distance, right?
Yeah.
So what do you think is the input distance here? 15, yeah, good. 15 centimeters over 20 centimeters, so that's equal to, well, yeah, it is. You're right, it is. So it's 3/4, right? So it's a mechanical disadvantage. We're actually putting in more force but getting out a little bit of extra distance from that simple machine, right? Okay, what about the next one? So the next one, it's going to be the input distance is going to be the input arm of the, right, the distance between the applied force and the fulcrum, right? So that's 4, divided by the output arm, which is the distance between the output force and the fulcrum. Agree? So for machine number 2, TMA2 equals 4 meters over 2 meters equals 2. Okay? What about the pulley system? What is it? No. What is it? No. Close. Oh. No. 5.
Oh.
How come?
That's how many are attached to the block.
Right. Okay, good, because it's the ratio of the lines supporting the load to the lines inputting the tension, right? Think about why. About why this is. If this is a good pulley system, these are well-oiled pulleys, right? And so what's going to happen if I have a little bit of extra tension here, what's this pulley going to do? It's going to move. Equalize the tension, isn't it, right? Does that make sense? It's going to twist a little bit, and so it's going to transmit that tension to this line equally. So whatever the tension is here, the same thing's going to happen there. But that happens again, because this pulley does its job too, right? And so it's going to transmit that tension to this line. And this pulley transmits it onto that line, this one to that line, this one to that line. And so all of these lines, if the pulleys are good pulleys, if they're perfect, if they're ideal pulleys, there's zero friction. And so the tension is equally transmitted to all of those, right? Think about this in terms of a free body diagram. Then what would be the forces acting on our red box down here? Well, I'm going to have, if the tension in this line is T, then it's going to be T plus T plus T plus T plus T, right?
Yeah.
So I'm just going to get all these tension vectors stacked up, 5 of them. Right. Those are all pulling up, and then the only thing pulling down is just mg, right?
Can you combine the tension vectors to be 5T?
Yeah, that's what it would be, is 5t. Exactly. So more importantly though, what's the theoretical mechanical advantage then again? 5, because I've got 5 lines out to 1 line in. Okay? That seems like magic, but that's the way a block and tackle works. Block and tackle is an incredibly useful machine. If you ever want to pull your car out of a ditch or something, this is the one you want. The block and tackle, you can do anything with a block and tackle. I mean, if you have enough movable pulleys, you can multiply the force as much as you want to. You ever see anybody pick a car engine up out of a car, right? What do they call that? Just they roll over a block and tackle, and they wrap a chain around that and wrap a chain onto the engine, onto the hoist, right? And then they just. But what do you notice when they do that? There's lots of pulleys on there, right? They got to pull a lot of chain though. They pick that thing up even just a little bit. That's pulling all this chain, and the engine's just creeping up, right? Because of course you pay for the extra increase in force. To increase the force by a factor of 5, I would have to pull 5 times as much rope over here, right? See what I'm saying? And probably much worse than that, because there is gonna be a significant amount of friction in the pulleys. That's the downside of pulleys is, you know, they're imperfect, there is some internal friction, right?
Yeah.
Okay?
We should create our own mousetrap. We should just buy a whole bunch of mousetrap games instead of.
Yeah, maybe. My grandpa was a really smart guy. He didn't have, he had, I think, a 7th or 8th grade education, but he was a really smart guy. He would have been a good physicist. He came up with an idea. This was pretty cool. He came up with an idea. He should have patented this. This is pretty good. He came up with an idea of a way to pull. This is how he did it. He pulled stuff into the back of his pickup truck. Here's how he'd do it. He'd tie a line up like to. So here's the pickup truck. Right. So there's the bed of the pickup. He'd tie a line up to like a tree. Right. So here's my tree. And then he had a ramp on the back of the car, and say, here's the object he wanted to pull into his car,
Yeah.
right? So what do you think he did?
Back that.
The log into the tree.
He put a pulley, if we look at the back of the pickup, like inside the bed of the pickup, he had a pulley back here mounted to the back of the truck, okay? He'd wrap a line around this thing so it went like this. He just drove forward. Isn't that cool? Well, you have to have something to hook the pulley to. But if you have a big long cable, I mean, you can find something. You can hook to another car or whatever, you know, right? And so you can get stuff into your car just by moving forward. You're going to drag this thing up the ramp and into the back of the pickup, right? Okay, so what if we wanted to then calculate the theoretical mechanical advantage of the whole mousetrap? What do you think we do?
Times them together.
You multiply them together. Yeah, you find the product of all the individual mechanical advantages. So all we'd have to do to find the overall mechanical advantage is just say, okay, so the theoretical mechanical advantage of the whole thing is going to be 3/4 times 2, right? That was the lever, times 5. Oops, boy, I'm running out of virtual ink again. So I'm going to get, what is that? So 30 over 4, so 15 over 2, so 7.5, right? So 7.5 is so theoretically, I should be able to push with 100 pounds of force and pick up something that weighs 750 pounds. Okay? Make sense? Okay? All right. Good stuff. So here's my challenge to you. Last issue challenge. You love challenge, right? So let's say do this again. Same dimensions. I like the dimensions. 2 meters, 10 meters. Here's we'll go 15 kilograms. Starting from rest, when it gets to the top of the ramp, it's moving that direction at 3 meters per second. Okay? And I have to input, let's say, 120 newtons. I'm inputting 120 newtons to slide it up the ramp. Okay? So the input force, or the pushing force, we'll call it F sub P. Okay? You got a picture? Okay, I want to know how much work is done by friction. That's a pretty good problem. Pretty sophisticated problem. Mm-hmm. What do you think? What can you tell me about it?
Well,
And
first
gravity
you
is
have
still
to.
a factor.
Yeah, oh yeah. This is on Earth, yeah. Gravity is still a factor.
shift the time to,
So let's throw some things out here. How can we do this? Some ideas. So it might be nice to know, like, what are the forces that do some work, maybe, right?
yeah,
So what are the forces that do some work? Gravity, yes, sure.
your Newton.
Say it again?
120 Newton.
Oh, yeah, so the
Okay.
pushing, right, whoever's pushing this up the ramp is doing some work on the, yeah. And friction's doing some work, and that's it, isn't it?
Yeah.
What about like the normal?
Okay, but the normal force is there, but the normal force, this object is moving up the ramp perpendicular to the normal force, right? So therefore, the normal force does no work, right? Because would you agree, because the direction of the force and the direction of the force, the normal force, and the direction of the displacement are at a 90-degree angle, and so FD cosine theta is going to give you 0, right?
Yes.
Okay. All right, so we've got those 3 objects. Is it possible for me, without even calculating any of those, to determine what the net work due to all those forces is?
Yeah.
What is it?
Change.
Changing kinetic energy. It starts from rest, and it ends up going 3 meters per second, right?
Yeah.
So we can calculate that. Delta K is just the final kinetic energy because it's starting from rest. So that's just 1/2 times 15 times 15 times 3 squared. 15 is a bad choice, but that's all right though. So that's going to be 7.5 times 9, which is what?
67.5.
Okay. 67.5 joules. That's the net work done, right? For sure.
Yeah.
Can we calculate the work due? We can't calculate the work due to friction directly because we don't know anything about the friction, right? But we know stuff about the other forces. You told me also that the push and gravity do work, right? So what's the force due to the push?
Distance times space.
I mean the work due to the push, sorry.
FD cosine theta.
Okay, and we don't even really have to mess with the cosine theta here because we know the direction, we know the force that's being directed
Parallel.
along the, how do I say this? We know that the pushing force is parallel to the surface, right? Okay, so that's simply equal to 120 times 10, right? Everybody agree?
Yeah.
Okay.
Why 10? Why not 2?
Because the pushing force is acting
Okay.
through 10 meters, right? Oh, sorry. Yep.
I tricked
Delaney.
you. I'm sorry.
He was gonna write the right answer though.
I was going to, that's the thing. 120 joules, pushing force, right?
Wait.
1200, I think. Just check it to see if you were here. Good. 1200 joules, good. So how about the work due to gravity? Now be careful with this one. Okay, the work due to gravity. So the work due to gravity must just equal the gravitational force times what? The distance along the lines of gravitational force, right? So what is the gravitational force? mg, exactly, that's it. Gravitational force is just weight, right? That's what gravitational force is weight. So that's just 15 times 9.8, let's just call it times 10. So that's 150 newtons, roughly, times what distance? 2, because the gravitational force is acting vertically, right?
Yeah.
The object is moving vertically
Oh, I get
only 2 meters, right? And we're looking for the displacement along the lines of that force, right?
Yeah.
So 150 meters times 150 newtons times 2 meters, but we got to be careful. What's the sign going to be?
Newton's a meter.
Negative. How come? You're right. Because gravity's pushing down and the vertical displacement is up. So we got to put a negative sign on there, right? So So that gives us negative 300 joules, right?
Yeah.
And if we add this stuff up, that plus the work due to friction should equal 76 or 67.5 joules, right? Everybody agree? Because
So-
that's what the work energy theorem tells us. The work due to all forces must always equal the change in kinetic energy, right? So we could solve for this one just by, subtracting, right? So what are we gonna get? Somebody figure this out. 67.5 plus 300. Well, actually, these two combine pretty easily, don't they? These two combine to 900, right? So 67.5 minus 900 gives us 832.5 joules.
Is it not negative?
That's the answer?
Negative, you're right. Negative, because we're subtracting 900 from 67.5. So the friction should be negative, of course. How come?
Because working against the force.
Yeah, because friction is always pushing in the opposite direction of the displacement, right? And so that's how much work is done by friction. Okay? Now I got a tricky one for you. This is a great question. It's gonna make you think. So what if we wanted to calculate the actual mechanical advantage of this ramp? What are we gonna do?
Um,
60.
What's that gonna be? So the actual mechanical advantage we always defined as the output force divided by the input force,
so
right?
your newtons, right?
Yeah.
Divided
Okay,
by-
yeah, but which output force? So the output force is what we actually accomplished, isn't it?
67.5.
Right? So what we actually accomplished was 300 joules. That's what we picked up, right? Because
Why?
we picked up, what we really accomplished was we picked up a 150 Newton object 2 meters.
Oh, I
Right.
see, yeah.
So that's the output force. We calculated the input force to be 1200 newtons, right?
Okay.
Make sense?
So we're doing more force?
So, right, so the efficiency wasn't very good, but is that accurate? Is that accurate? Something's wrong with that.
Yeah, cause it would be.
Something's wrong with that. There's something different. I'm gonna try to point it out to you. What if we pushed with instead a 240 newtons of force? If we pushed with 240 newtons of force, the speed would have changed at the end, right? And it would have looked like we input a lot more work. Agreed?
Yeah.
But did we really do any extra work compared to the output work? No, we didn't. We didn't, right? Do you see what I'm getting at? If I push with 240 newtons, I'm still pushing through 10 meters. It's gonna look as though we did 2,400 joules of useful work. And we did, but that's not a fair measurement to make in comparison to the output work, right? And how come not? Because we did really two things here, didn't we?
Moved it faster.
Yeah, we made it faster. We did two things. We did work against gravity, where we increased the gravitational potential energy of the load, right? And that's the part we should compare to this, right? See what I'm saying? But then another part of this, above and beyond that, invested some kinetic energy in this thing that really we shouldn't be comparing. Everybody see what I'm saying there? Right? If we want to look at what the efficiency of just the machine is, what we'd really like to do is we'd like to take the situation, make it a little different. We'd like to push this thing up at constant speed
Yeah.
so the kinetic energy didn't change, right? But unfortunately, the movie that we're watching here has this thing increasing its speed. We could still make this calculation. What could we do? What could we do? If we want to make an estimate of the actual efficiency, we don't want that extra speed. Well, what we'll do is we'll subtract it from the amount of work that we did, right? Agreed? Because the work that we did, the 1200 joules, 67.5 of that was to increase the speed, and the rest of it was just to move it up the ramp.
Okay.
See what I'm saying? So what we could do is take that 1200 joules and subtract away the additional kinetic energy, and then make our ratio, right? So what we'd really get is the useful work, so the efficiency would equal, what did we say it was, 300 joules? Pick it up, yeah, 300 joules of output work divided by 1200 joules minus 67.5 joules. So we're just getting the work that we did against gravity.
So it's actually very good.
It's not very good.
Would you keep the 300 negative?
No, we wouldn't in this case, because, right, because all we're doing is we're looking at the amount of work that was done out of the machine, and the output work of the machine. What we really accomplished was we lifted a load up 2 meters, right? Okay. That make sense? That's pretty tough. I mean, that's a
Yeah.
pretty hard problem.